Hello everyone, welcome to my channel. Please like and subscribe. In this video, we'll be learning how to design a continuous beam. A continuous beams are those beams that extend over more than two supports. These supports can be two supports, three supports, four supports, and so on. During the design of continuous beams, there are various steps are to be followed. Now, in your problem, which states that a continuous beam is 300 millimeter wide by 6 deep with equal span of 5.5 meter, means that these beams have a section of this way, which have a width of 300 millimeter and overall depth h, which is equal to 600 millimeter. A continuous beam of 3 equal spans means that, let's say, this is 3 continuous beam, first continuous beam, second beam, this is third beam, span number 1, span number 2, span number span number 3. This is a continuous beam of 300 millimeter wide and overall depth, which is deep 600 millimeter, with 3 equal spans: span number 1, span number 2, span number 3, with of 5.5 meter and 5.5 meter, 5.5 meter. In the transfer directions, the beam at 4 meter centers with the thickness of this one, means that from the center to the center of this continuous beam, there lies 4 meter with a thickness of 180 millimeter thick slab, means that the thickness of this slab is 180 millimeter. The leaf and the leaf load, which is imposed load QK, is 50 kilonewton per meter. And imposed load, which including self weight, is 85 kilonewton per meter. The characteristics material strengths are, which are FCU concrete strengths, is 30 Newton per millimeter square, and reinforcement strength is 460 Newton per millimeter square. Assume the concrete cover is 25 millimeter, and link diameter is 10 millimeter, and the main bar diameter is 20 millimeter. Now, when we cut this section so as to make transverse direction, it will be, let's say, we cut the section at this way. Let's say this section A. The output, it will be in this way. This is beam number 1. It will be in this way. Which was span of 5.5 meter, 5.5 meter, 5.5 meter. From the center to the center of this span is 4 meter. Now, as this section it have two types of beams. It have L beams, and T beams. L beams, which are edge beams. Let's say when you cut at the center of this span, this is L beams and this is T beams. From the center to the center is 4 meter. Now this is the width from the center up to this center is 2 meter plus the 2 meter from this center. So it makes this is effective flange width, which is makes of total of 4 meter, since because from this center to this center of this beam is 4 meter. Now the same a half of this length is 2 meter. 2 meter and this 2 meter makes a 4 meter. Now this is effective flange width of this T beams. Now, and this is the web width, which is equal to the width of this beam. This is web width, which is equal to width of the beam, which is 300. Now, effective flange width of this beam is 4 meter, and this is actual flange width, and web width, which is equal to width of the beam is 300 millimeter, and overall depth is this one, 600 millimeter. Now, when you draw the bending moment diagram of this continuous beam, it will be drawn this way. Bending moment diagram, it will be drawn this way. Since it have, let's say it have support number 1, number 2, number 4, so it will be support number 1, support number 2, support number 3, support number 3. Now, its bending moment diagram, it will be drawn this way. The bending moment diagram will be drawn this way. Now, for continuous beam, negative moment occur at supports. Now, this is negative moment which occur at supports, at interior supports. This is negative moment, and the positive moment occur at mid-span. This is positive moment, and this is positive moment. Negative moments, sometimes known as hodging moments, occur at supports, occur at supports, and the reinforcements are provided. This is this is top reinforcements. Negative moment, top reinforcement. The reinforcement should be provided, so it's known as top reinforcement. Top reinforcement. And positive moments, sometimes known as surging moment, which occur at mid supports, which occur at mid-span. Surging moment. This is surging moment. Surging moment occur at mid-support, occur at mid-span. This reinforcement provided at surging or positive moments, where is found at mid-span are bottom reinforcements. Now, how to determine the maximum designing moment at mid-span and the maximum at mid-span and at supports. This maximum design moment are determined by using BS 8110 part 1 1997 table 3.5. Table 3.5, this one. At the outer supports, let's say at this is outer support, and this is outer support, and this is anterior supports. Now, at outer supports, moment at outer support is 0. So moment at this point is 0, and and the moment near mid of the end support at this span, near mid of the end span. This is near mid of the end span. At this point, maximum design moment is equal to 0.09 FL. So at this point is 0.09 FL. Since continuous beams are arranged in symmetrical means, so the maximum design moment at this span it will be equal to maximum design moment at this span. Since it is symmetrical, the span at this support at the same with this span. So the maximum design moment at this point is also 0.09 FL, similar to this at interior supports. At the first interior supports, the maximum design moment, which is at negative moment, is 0. Is at this point is similar to this point since they are symmetrical arrangement. So it will be equal to 0.11 FL. Similar to this point is 0.11 FL. And the maximum moment at the middle of the interior supports. This is the maximum moment at the middle of the interior span. This is the middle of the interior span. The maximum design moment is 0.07 FL. Now, this is how the maximum design moment is obtained from the BS 81110 part 197. Now, before designing this moment, there are various steps to be followed during designing of this continuous beam. Step number one is to determine design load. Design load. Design load is per BS 8110 part 1 1997. Design load is given by 1.4 times dead load plus 1.6 times imposed load. Now design load it will be equal to 1.4 times dead load, which is equal to 85 plus 1.6 times 50. Now design load it will be equal to 1.4 times 85 plus 1.6 times 50. It will be equal to 199 kilonewton per meter. The next step is to determine design load on spans. Design load on spans. F. Design load on spans. At each span, the design loads. Now, design load on span is given by taking design load times the span of each span. Now, the span of this continuous beam is 5.5. Now, design load on span will be equal to 199 times span, which is 5.5. Now F it will be equal to times 5.5. It will be equal to 1094.5 kilonewton. The next step is to determine the maximum design moment. The maximum design moment, let's say at from this bending moment diagram, when we're designing, we consider two cases. At interior supports, you're supposed to design as a T section, where width of this beam will be equal to effective flange width, and at mid supports, at mid span, design as a rectangular section. Design as a rectangular section where width it will be equal to web width. As this during designing this continuous beam, these are tips should be considered during designing. Now, let's say at mid span. Let's start at mid span. At mid span of first and said span. This one. Now this is first span, which is equal to 5.5. Second span from this support to this support. This is second span, and this is third span. Now, for case A, we design at mid span of first and third span. Means that at mid span, at this mid span and this mid span. At mid span, we design as T section. Design as T section. At this mid span, maximum design moment is obtained by taking 0.09 FL, maximum design moment. Now, maximum design moment, it will be equal to 0.09 times F, which is 1094.5 times L, which is 5.5. Now, maximum design moment, it will be equal to times 0.09 times 5.5. It will be equal to 541.78 kilonewton meter. Now, since we design as a T section, the next step is to determine effective flange width. 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 Effective flange width is obtained by taking the less of actual flange width, which is actual flange width from this section, from this T section, is 4 meter. Is 4 meter, which is equal to 4,000 millimeter, or web width plus, for continuous, this is T section, it will be equal to LZ over 5. But LZ for continuous beam, but LZ is equal to 0.7 times L. Now web width will be equal to web width plus 0.7 times span of this continuous beam over 5. Now web width is 300 millimeter. Is 3 millimeter. The width of this beam plus 0.7 times span, which is 5.5 meter, which is equal to 500 millimeter over 5. So it will be equal to 0.7 times 5500 divided by 5 plus 300. It will be equal to 70 millimeter. Now, effective flange width is obtained by taking the less among these two. Active flange width or web width plus LZ over 5. Now, the less among these two, this is 4,000, this is 50,000. Now, the lesser is now effective flange width, it will be equal to 70 millimeter. 70 millimeter. The next step is to determine the position of a neutral axis. The position of a neutral axis. Position of a neutral axis. Position of a neutral axis. If x is less than the thickness of that slab, which is equal to 18 millimeter, then the flange width, the neutral axis lies within the flange. If the neutral axis lies within the flange, so your design is a single reinforced section. Now, how to determine the value of x? X is determined by taking effective depth minus z over 0.45. But effective depth is obtained by taking overall depth minus concrete curve minus link diameter minus main diameter over 2. Effective depth will be equal to overall depth is this one, 600 millimeter. 600 concrete cover we have given is 25 minus this one, concrete cover is 25, link diameter is 10 millimeter, and main diameter is 20. So link diameter is 10 minus 20 over 2. Effective depth it will be equal to 55 millimeter. Now, how to determine the value of z? The value of z is obtained by taking effective depth times 0.5 plus 0.25 minus k over 0.9 under root. And this should be less than equal to 0.95 times effective depth. But k is equal to maximum design moment over 0.95 over FCU BD square. K it will be equal to maximum design moment, which is equal to 541.78 kilonewton meter, which is equal to 10 power 6 Newton millimeter over FC, which is 30 times beats. Beats for this section, beats will be equal to flange width, which is equal to 1070 millimeter. Now it will be equal to 30 times 1070 times effective depth, which is 555 square. It will be equal to 541.78 x.6 divided by 30 times 1070 times 55 square. K, the value of k, it will be equal to 0.0 0.05. Hence, the value of z it will be equal to effective depth times 0.5 plus 0.25 minus k, which is equal to 0.05 over 0.9 under root should be less than equal to 0.95 times effective depth. The value of z it will be equal to 0.93 times effective depth. This is less than 0.95 times effective depth. Hence, the value of z will be equal to 0.93 times effective depth, which is equal to 555. The value of z it will be equal to 0.93 times 555. It will be equal to 516.15 millimeter. Now, the value of x will be equal to effective depth minus z over 0.95. X will be equal to effective depth is 5 minus the value of z, which is equal to 516.15 over 0.45. It will be equal to 86.33. X, it will be equal to 86.33. This is less than 180, which is HF millimeter. Since X is less than HF, the thickness of slab, hence the neutral axis lies within the flange. Hence, design as a single reinforced section. Design as a single reinforced section where the area of single reinforced section provides the tension reinforcements only. Now, the area of tension is obtained by taking maximum design moment over 0.95 Fy times Z. Now, area of tension will be equal to maximum design moment. Maximum design moment is this one, 541.78. 541.78 exponent 6 over 0.95 times Fy, which is equal to 460 times Z, which is equal to 516.15. Area of tension, it will be equal to 541.78 exponent 6 divided by 0.95 times 460 times 516.15. It will be equal to 4. It will be equal to 4. It will be equal to 402 millimeter square. This is area required for this design as T section. Now, to determine the number of bars required for this T section at midspan of first and second, at first and third span, to determine the number of bars and area provided, we use this table. Since the area required is 24, 0.8. Now, from this table, this is the number of bars and this is the bar diameter. Now, we check the area which correspond to this area and should be greater than the area which is greater than this one and should be closer to this one. Now, our area required is 24,002 millimeter square. Now, the area which is greater than this one is 24,10 millimeter square, which provides the number of bars of 3 with a diameter of 32. Now, the tension provides 3 bars with a diameter of 32, which gives the area of tension which is equal to 2410 millimeter square. And as previous, I said that at midspan, the reinforcement provided at bottom reinforcement. So this is bottom reinforcement. This is bottom reinforcement. Bottom reinforcement. This is bottom reinforcement, but at interior supports, the reinforcement provided at the top because they are negative. And this is bottom reinforcements because provided, this is a positive provided at, this is bottom reinforcement because it gives surging moment at midspan. That's why bottom reinforcements. Now case B at interior supports at interior supports at interior supports design as a rectangular section. It's a rectangular design is a rectangular section. Design is a rectangular section. At this section, the width of the beam will be equal to web width, which is equal to this one, the width of the beam, which is 300 millimeter. Now at interior support, this is interior support as this one, and the maximum design moment at this interior support is at interior support, since it is metric arrangement, as the maximum design moment at this support and this support is similar. Now its maximum design moment, it will be equal to 0.11 times FL. Now maximum design moment, it will be equal to 0.11 times F, which is times F, this one, 10 94.5 times L, which is 5.5. Now maximum design moment, it will be equal to 0.11 times 1094.5 times 5.5. It will be equal to 662.17 kilonewton meter. Now, since we design is a rectangular section can be single reinforced section or double reinforced section. Now, we're supposed to determine and to know does its design lies within a single reinforced section or double reinforced section. This section checked by using this. If K is less than K dash, since is single reinforced section, but for double reinforced section, if K is greater than K dash, this is double reinforced section. This is double reinforced section. Double reinforced section. Double reinforced section. Now, the value of K is obtained by taking maximum design moment over FCU BD square. Now K is equal, it will be equal to the value of K is obtained in previous. The value of K maximum design moment is this one, 662.17 exponent 6, so as to make in Newton millimeter over FCU. FCU is 30 times Blitz. Blitz is 100 times effective depth, which is 555 square. Now the value of K, it will be equal to 6 62.17 exponent 6 divided by 30 times 300 times 55 square. It will be equal to 0.24. So since k is equal to 0.24 and this is greater than 0.156, k is greater than k dash, means that design is double reinforced section, design is double reinforced section, double reinforced section. Double reinforced section, both compression and tension reinforcement are provided. Both compression and tension reinforcement are provided. Now, how to determine the compression reinforcement? Now, first of all, you are supposed to determine the area of compression. The area of compression is obtained by taking maximum design moments minus ultimate moment of resistance over 0.95 Fy times effective depth minus effective depth of compression. But ultimate moment of resistance is equal to 0.156 FCU BD square. Now, ultimate moment of resistance, it will be equal to 0.156 times FCU, which is that, times breadth, which is 300, times effective depth, which is 555 square. So they are in millimeters. So to make it in kilonewton meter, we multiply by 10 power negative 6. Now, ultimate moment of resistance, it will be equal to 0.156 times 30 times 300 times 55 square times exponent negative 6. It will be equal to 432.47. This is kilonewton meter. But effective depth at compression region is obtained by taking overall depth minus effective depth. Effective depth at compression overall depth is 600 minus effective depth, which is equal to 55. It will be equal to 45 millimeter. Now, the area at compression, it will be equal to maximum design moment is equal to maximum design moment at this case is equal to this one, 662.17 minus ultimate moment of resistance, which is equal to 432.47. Since they are in kilonewton meter, we multiply by 10 power 6 over 0.95 Fy, which is equal to 460 times effective depth, which is equal to 55 minus 45. Area at compression, it will be equal to 662.17 exponent 6 minus 432.47 exponent 6 divided by 0.95 times 460 times 55 minus 45. It will be equal to 1031 millimeter square. This is the area required for compression reinforcements. But how to determine the number of bars? The number of bars required at this compression reinforcements. Since the area required is 1031 millimeter square. Now, from this table, we'll be able to determine the number of bars required and the area provided at this region. Since the area is 1031, now we check 1031. So, lies at this 2 bars. It gives the 2 bars with the area, which is the area should be greater than this one now, and should be closer to this area. The area which is greater and closer to this one is this one, which gives now provides the compression provides two bars with a diameter of 32 millimeter, which gives the area of 1610 millimeter square. This is the area of compression. The area of compression. Now, the next step, since double reinforced section provides both compression and tension reinforcements. Now, the next step is to determine the area of the area the area of tension. Now this is bottom reinforcement. Bottom reinforcement. Bottom reinforcement. Now the next step is to determine the area as a tension reinforcement. The tension reinforcement, first of all, to determine the area of tension. The area of tension is obtained by taking ultimate moment of resistance over 0.95 Fy Z plus the area of compression. The area of compression. Now, area of tension will be equal to ultimate moment of resistance is this one, is 432.47 exponent 6 over 0.95 times Fy, which is equal to 460 times Z. The value of Z is this one. The value of Z is this one. The value of Z is this one, 516.15 times 516.15 plus the area of compression, which is this one, the area required, which is equal to 1031 millimeter square. Now the area of tension, it will be equal to 432.47 exponent 6 divided by 0.95 times 460 times 516.15 plus 1031. It will be equal to 2948 millimeter square. This is area required at tension reinforcement. Now, how to determine the bars required at these zones and the area provided. Now, to determine the bars required from this table, we'll be able to determine the bars required. Since the area required is 2948, so we check the area which corresponds, which is greater than this one. It will be equal to, it will give 4 bars, hence provides 4 bars with diameter of 32, which gives the area of tension, which is equal to this one, 3220 millimeter square. This should be at, since we were designing at interior supports, the reinforcement should be provided at top reinforcement, at top. So this is top reinforcement. Top reinforcement. As previous I said that at interior supports, which are negative moments, sometimes known as surging moments, the reinforcement should be provided at top because are negative. Now, the next step is to determine design at all of this one. We have designed at mid support and at interior support. Remains the design at interior mid support, at mid span, at mid span of the second span, of the second span, of the second span. Maximum design moment at this span. Maximum design moment at mid span, we design a ST section. We design a ST section where web width as the width of the beam is equal to flange width, which is equal to 1070 millimeter, and the value of Z was 516.15 millimeter, and the value of K. Okay, as the maximum design moment at the middle of the interiors, at the second span, maximum design moment is 0.07 FL. Now, maximum design moment will be equal to 0.07 times F, which is equal to this one, 10, which is equal to 1094.5 times L, which is 5.5. Maximum design moment, it will be equal to 0.07 times 1094.5 times 5.5. It will be equal to 421.38 kilonewton meter. Since we design a ST section, we'll base as the next step is determine effective flange width. Effective flange width is we have calculated which is 1070 millimeter. And the next step is to determine the position of neutral axis. The position of neutral axis is determined by checking if x is less than hf, meaning that we design as a single reinforced section. The neutral axis will lie within the flange. Since the value of x we have obtained, which is obtained by taking effective depth minus the value of z over 0.45, we will obtain which is 86.33. This is less than 180 millimeter. We design as a single reinforced section. Design as a single reinforced section. Reinforced section means that no compression reinforcement should be provided, and the tension reinforcement only are provided. Now, how to determine, since the tension reinforcement are provided, the next step is to determine is the area of tension. The area of tension is obtained by taking maximum design moment over 0.95 times FYZ. Now, area of tension will be equal to maximum design moment we have calculated, which is this one, 421.38 exponent 6 over 0.95 times Fy, which is equal to 460 times the value of Z, which is 516.15. Now, the area of tension, it will be equal to 421.38 exponent 6 divided by 0.95 times 460 times 516.15. It will be equal to 1868 millimeter square. Now, to determine the number of bars required, the number of bars provided should be provided at this tension reinforcement, and the area provided, we use this table. Since the area required is this one, to obtain the area provided and the number of bars should be provided. We check the area which is greater than this one and should be closer to this one. The area provided. Now this is area should be provided. And this is greater than this one and is closer to this one. Now the tension provides three bars. This one, 3 bars with a diameter of 32, which gives the area of tension, which is equal to 2410 millimeter square. Since we are designing at mid span of the second, at mid span, the reinforcement should be provided at bottom. Now this is bottom reinforcement. This is bottom reinforcement. Thank you for watching this video. Please like and subscribe for more civil engineering contents.